Hi, welcome to your Chapter 16 video number 1 for AP Statistics. If you hear someone snoring softly in the background, it's Scout, my little dog, and her sister Daisy is here with us too, but Scout is definitely the snorer. I'm a little congested, but it's not me who's snoring. Okay, so Chapter 16 is all about random variables. And random variables are different than algebraic variables. Okay, a random variable assumes the value based on the outcome of a random event. So it might be the outcome of a single roll of a die. So then your random variable could take on the value of 1, 2, 3, 4, 5, or 6, depending on what the outcome of the die is. So it's a little bit different concept than an algebraic variable. We use a capital letter, like capital X, to denote a random variable. A particular value of a random variable will be denoted with the corresponding lowercase letter, in this case, little x. There are two types of random variables, discrete random variables, and they can take on one of a countable number of distinct outcomes. So, for instance, the number of credit hours. We can look at the number of possible credit hours students can take, and so they might be able to take 1, 2, 3, 4, 5, 6, 7, 8, up to 21. Maybe that's the maximum number. But we can count how many outcomes there are. Another way to think of it is there's distance between the outcomes that can occur. Continuous random variables can take any numeric value within a range of values. So, for example, height of adult men. Now, we may be limited by the tools that we have to only be able to get to the nearest tenth of a centimeter, so on, but the actual heights themselves can get as close to each other as you'd like, and even closer than what you can conceive. There is no demarcation between one possible height and the next. A probability model for a random variable consists of the collection of all possible values of a random variable and the probabilities that those values occur. And they do need to add up to 1. So that's something important about any probability model. Of particular interest is the value we expect a random variable to take on, notated rather as mu for the population mean, or E of x for expected value. So mu and E of x, mean and E of x, same thing. Expected value and mean, exactly the same thing. So the way that we find that for a discrete random variable is we sum the products of each possible value by the probability that it occurs. So mu or E of x, same difference, is equal to big sigma, okay, the big sigma denoting summation, of x times the probability of x. So for each possible value, we take that value and multiply by its probability of occurring, and then we add the next value in terms of probability that it occurs, and so on. Note that you need to be sure that every possible outcome is included in the sum and verify that you have a valid probability model to start with. In other words, you need to make sure all the probabilities add up to 1. For data, we calculated the standard deviation by first computing the deviation from the mean. So y minus y bar or x minus x bar, each observation from the mean of the data, and then we squared it. We'll do the same thing with discrete random variables as well. So the variance for a random variable is baby sigma squared, so sigma squared equals the variance of x equals big sigma times x minus mu squared. There's our square of the deviations times p of x. The standard deviation then is just the square root. So you take the square root of the variance of x, and that'll give you standard deviation or SD of x. Okay, we can add and subtract random variables, or we can add and subtract constants to them. Adding or subtracting a constant from data shifts the mean, but doesn't change the variance or the standard deviation. So the expected value of x plus or minus c, so we're going to add or subtract a constant, is equal to the original expected value plus or minus that same value c. The variance of x plus or minus c is just going to be the variance of x. You're not going to increase or decrease the variance within the values. So, for example, consider everyone in a company receiving a $5,000 increase in salary. Okay, that would be great because the average salary would just go up by $5,000. You just add it to it, but there would be no greater variance among the values. But if, for instance, if you took the range of the highest salary minus the lowest salary, that would be exactly the same. Since they were both increased by 5,000, when you do the subtraction, the 5,000s would cancel each other out. Okay, so we added and subtracted a constant. Now let's multiply each value by a constant. So in general, multiplying each value of a random variable by a constant multiplies the mean by that constant and the variance by the square of that constant. So if I have the expected value of a times x equals a times the expected value of x, that makes it a lot easier because you can just take the old expected value of x and multiply it by whatever your factor is. Variance of a times x is a squared times the variance of x. So consider everyone in a company receiving a 10% raise. Then really you're multiplying their old salary by 1.1 because the 1 represents the original 100%, the 0.1 represents the 10% increase in salary. So you would take the old expected mean, or expected value, not expected mean, the mean or expected value, and you'd multiply it by 1.1. For the variance, you would take the 1.1 and you would square it, and then that would give you the value you need then to multiply by the variance of x, which then means the standard deviation is multiplied by a, or the absolute value of a. So in general, the mean of the sum of two random variables is the sum of the means. Okay, so this isn't adding or subtracting a constant. This is you're doing two random variables. The mean of the difference of the two random variables is the difference of the means. So e of x plus or minus y is e of x plus or minus e of y. So if I was doing the sum of the outcomes of a red die and a green die, then and let x be the outcome of the red and y be the outcome of the green, then I would just find the expected value of the roll of the red die and the expected value of the roll of the green die, and I would add them together. If the random variables are independent, the variance of their sum or difference is always the sum of their variances. So variances add, standard deviations do not. If you're asked for the standard deviation, you find the variance of x plus y or x minus y first, and then take the square root. All right, continuous random variables. Random variables that can take on any value in a range of values are called continuous random variables. Now, any single value won't have a probability, but you can still find the mean, the expected values, and the variances. We won't worry about how to calculate these means and variances in this course, but we will still work with models for continuous random variables when we're given the parameters. So you have to be given the mean and the standard deviation, or the mean and the variance. Good news, nearly everything we've said about discrete random variables behave the way discrete random variables behave is true of continuous random variables as well. When two independent continuous random variables have normal models, so does their sum or difference. This fact will let us apply our knowledge of normal probabilities to questions about the sum or difference of independent random variables, and we'll see that in just a minute. So what can go wrong? Probability models are still just models. Models can be useful, but they are not reality. Question probabilities as you would data, and think about the assumptions behind the models. If the model is wrong, so is everything else. Don't assume everything's normal. You must think about whether the normality assumption is justified. Watch out for variables that aren't independent. You can add expected values for any two random variables, but you can only add variances of independent random variables. Don't forget that variances of independent random variables add, standard deviations do not. And don't forget, variances of independent random variables add even when you're looking at the difference between them. So even if you're looking at the difference, x minus y, you're going to add the two variances together. Don't write independent instances of a random variable with notation that looks like they are the same variables. We're going to have an opportunity to look at that in one of our examples. So we've learned how to work with random variables, and we can use a probability model for discrete random variables to find its expected values and standard deviation. The mean of the sum or difference of two random variables, discrete or continuous, is just the sum or the difference of their means. And for independent random variables, the variance of their sum or difference is always the sum of their variances. Normal models, once again, are very special. Sums or differences of normally distributed random variables also follow normal models. Okay, this is it for this portion of our lesson. You'll come back in the next video and do the examples. I will be back with you in just a few minutes.